and welcome to the Zephyr meetup. My name is Saravanan. I'm part of Linamus. So, in this session, we are gonna see what is EVSE, electrical vehicle supply equipment, which is used for the electrical vehicle charger, and what is the requirement of real time in the charger, and how does the Zephyr RTOS gonna help with the charger for the real time operating system meetup for the real time requirement. So myself, I'm Saravanan, and I'm a software developer, and I have worked around past 12 years in in the area of Linux kernel, Zephyr RTOS, and then automotive sector. And I'm part of Linux. And yeah, I live in Berlin, Germany. So this one probably my colleague have already explained about what our company does and all the advertisement factors. Let's dive into the actual topic. Here, first we will check what is the electrical vehicle, and then the charging infrastructure. What is the requirement, and how does in comparison with the existing fuel in or the gasoline system. Okay. So the electrical vehicle, which runs basically based on the battery driven or the electrical supply as the source. The contrast with the existing fuel in or the gasoline system, the amount of time to refill the gasoline or the petrol is less than a minute and does not take much time for the parking in the gas station also. But in the contrast, for the electrical vehicle, it needs a lot of time to recharge the battery, and it is not fit the conventional gas station like infrastructure, because the vehicle has to be parked next to the electrical charging station for multiple hours, and one bulkier system kind of the gas or the fuel station will not help here. Instead, it needs it's need distributed lightweighted infrastructure, almost like every parking lot, or wherever, let's say if we have a malls or shopping complex or somewhere where it will be parked, there we need the charging infrastructure as a distributed one. And hence the EVSE, the electrical supply equipment, needs to be portable and easy to install in a smaller one. And the requirement for the electrical vehicle supply equipment is like, we have a wide range of vehicle, from the two-wheeler or the bigger three-wheeler or bigger car. And even we have now we have the buses which is running on the electrical vehicle. So the amount of time which takes depends, and also the categories different. So in case of a US, we have it is categorized as three phases. The phase one, which is charging capacity, is a lower, in the range of under 2 kilowatts, and phase two, which is they're capable of 20 kilowatts, and there is a higher end, which is the DC charging system, which is the advanced and fast charging system which is available. But as I said, we have the different range of electrical equipment, and the requirement for the charging station also differs. So we need the more and more distributed EVSE or the charging station. Okay, here we have the common setup of what is the electrical vehicle supply equipment applies. It is split into two things. One is for the charge point or the charger, and then the charge point or the charger itself, and then there is a electrical vehicle, and there is another part which is the charging system, which communicate back to the central system or the server. What is the need of that? We'll explain it shortly. And this can be divided into two things. One is for the real-time needs, and there is another one which is not as a real-time requirement needed. The charging system, what we are discussing right now, is the publicly available one, or the publicly deployed one, and it should be the vendor neutral. For example, the charger manufacturer can be company A or B, and then it should support the vendor like A to Z or something like that. So because of that, the electrical vehicle manufacturer can be of any company, and it can utilize the charge point from any vendor. Let's say I have the Tata and other vehicle, and I want to get the charging, and yeah, the payment system and other things also, there is a 2 3 providers may be available. So it should be the vendor neutral, and I should able to manage all the backend system and how the payment system and the authorization, everything is handled from the central system. So for that, there is a one common open protocol which is called OCPP, Open Charge Point Protocol. This is open standard which is adapted the worldwide. The open standard, the specification generally tells about if any user wants to get a charging from that charge point, first they have to get the authorization, and then they have to initiate the charging either from the system, like a press button or something available inside the charger, or else from the remotely, like I have a mobile phone, and where I can push a start button, and then it will goes to the charge system, central system, and then it will tell the charge point, okay, now you are authorized user, you are able to deliver power to this, yeah, EV, which is capable of, like the charger is capable of delivering the demand power by the EV vehicle. This is one point. So that's the reason I told you that this is a non-critical or the not real-time requirement here, because here we need the open charge point protocol, which is basically need a WebSocket communication, HTTP. So it will communicate back to the server. And then the other portion which we need is uh, the electrical vehicle and charge point connection, which needs to be in the real time. Why? Because the charge point needs to be shut down the power once it has any overcurrent detection or else the faulty detection and so on. For that, it has to be addressed immediately to stop or shut down the power. Okay, and that is even without this open charge point control in the central system, the other protocols like IEC 61851, which offer another uh, kind of a protocol, which is like plug and charge. Like when I have a electrical vehicle which I wants to plug directly to the charge point without having following all this process of start, charging, authorization, and so on, it directly delivers the power. And this IEC 61851 or ISO 15118, which will tell it, which will tell us what is this plug and charge mechanism. It is not like unauthorized power deliver. Even it follows a authorized power deliver, but it is pre-authorized by um, certificate already handshaking with the means of certificate and the public key infrastructures. So for that, yeah, even without the open charge point control and the central system, it can, the standalone can be achieved with just plug and play using the other protocols, charge point and EV, which is comes under again the real time system. So how does Zephyr RTOS help in case of this real time activities? As I said, the other the requirements from the modern EV charging standards or the load balancing. If I have a charge station which can be um, deliver or the charge parallelly by 2 3 vehicle and it has to monitor how much the power, incoming power, and how can it can be distributed at a time. If it has only one vehicle, which then it can deliver up to the 20 kilowatts. Maybe if I have another one, the input is restricted to 20 kilowatts, then I have to downgrade or split into the 10 kilowatts each. So these kind of mechanism of the communication between the EV and charge point has to be done. And also, as I said, if the EV vehicle is drawing a more power, then it has to shut down immediately. And also the input side monitoring on the meter, how much the power is being drawn, and all those things has to be real time. So for that, Zephyr RTOS is suitable, which is lightweight and modular, and also, yeah, it gives the deterministic control over controlling of all these functionalities. Okay, so as I said, there is a three categories. One with lower capacity of EV, and then the higher capacity. With a lower capacity of EV, let's say for the two-wheelers or the three-wheeler kind of a lower capacity vehicle, where we can use the microcontroller as electrical vehicle supply equipment without having high-end Linux or kind of infrastructure with Zephyr RTOS alone. So, what are the functionality that is needed to achieve this? Zephyr RTOS as standalone controllers. Again, as we talk about the OCPP, the Open Charge Point Protocol, which is needed to communication back to the central system and the CS, and also the central system can be connected to the mobile phone application or something, so that there is a communication which will trigger whether the user is authorized before delivering the charge, or when has to give the start charging. When I press the button, then it has to initiate the start transaction and so on. So for that, currently from the Linux, we have developed from the open specification document, we natively implemented this open charge point protocol using the WebSocket already available on the Zephyr, and we have attempt to raise the PR already in review. But one of the challenges, there is a dependency of the JSON, because the open charge point protocol says the message has to be the predefined messages over there, and that has to be in a JSON format. And yeah, the Zephyr RTOS default JSON is limited, like it is not flexible to have runtime memory allocation. It does not support those features, and what we have done for our customer is we used the flexible external JSON modules, so we have to port it back again, and yeah, clean up the PR which is in the pipeline. So at least I can say that open charge point protocol from the Linux is kind of already supported, even though it is not merged to the Zephyr, which is functionally we have tested, and we have in-house also developed the different TLS support and other activities for our customer, which is available in Linux GitHub. So this open charge point protocol is, again, it's an application protocol. It is not like sitting in the down like a TLS or something. It's specific to this charge protocol, and it relies on the TLS and JSON, as I said, JSON RPC messages. So which of the blocks are this one, the open charge point protocols. So other support, thanks to Zephyr RTOS, we support the other the stacks and the Ethernet or the network connectivity. For example, so because since we are aiming to have the EVSE using standalone Zephyr and the microcontroller, the only thing which is pending or unusable is the open charge point protocol, which is not implemented in that. In contrast with the Linux, we have the EVSE company which does, but it is not in the um, C language, or it is not directly compatible with the Zephyr as it is. So we have to implement natively from. Okay, so if you want to develop a very lightweighted for two-wheeler kind of a charging station, which is very simplified, which doesn't need a kind of a rich UI and customization, all these things is not needed, then the people can go with a lower capacity of thing, because we need the distributed. It's not like one big server kind of charger which can handle hundreds of car, because we need parking space, so we need a more and more distributed lightweight. That's the aim of that. Is that answers my? So when it is two-wheeler, you're saying about the CPP. It is not just limited to two-wheeler. I'm saying it's about the how many. Even you can use it for the single car with the But when you want a more distributed one, we can go with the Zephyr and the microcontroller one.
But this OCPP is common, right?
Yeah.
Like even in the Linux, it is OCPP.
Yes, that's true. It's an open standard.
And there are other portions of EVSE which is not open source because the specification itself needs to be brought from the respective standards, and those implementations cannot go open, and even any form of companies cannot go open of that level. So what is placed in here is like as a stack, it can be plug and play for a simple purpose, and whether you achieve a rich use case with a large set of UI and other things, or you wanted to just play around with the basic one. So if you just play around with simple functionalities of OCP, you don't need to go a rich set of hardware to build around ecosystems or something. So this OCP is what the connectivity to Linux because EV is like connectivity to the but can I take this implementation?
This implementation as in we cannot take it because we need again it really depends on the underlying interfaces, Ethernet or so on. Okay, there is some kind of adaptation which is needed, and then we can be able to use it because the OCPP stack already has implemented with the different layers. So when we move on that WebSocket layer, which is the down layer, so when we replace that WebSocket from the native Zephyr implementation to the socket-based Linux implementation, then it should be possible to use it.
So here you are consuming the HTTP for the WebSocket implementation.
Yeah.
So OCPP doesn't require real-time functionality, right?
Yeah. Yes. But today's talk is about how the real-time requirement. What is the real-time requirement on the charger, and how does this Zephyr helps with the real-time operating system, or how does it meet the real-time requirements for the chargers?
The automotive products mainly for the standards like that.
Yeah.
So if you are putting this label on this product, is customers can use this.
Okay, it's a big question again. Does this charging infrastructure really comes under the automotive sector? Because we have a fueling or the gassing system as well, which we are not considering as a automotive sector. Yeah. But for sure, it should be uh, secure communication, which is enforced by the ISO standards. The communication between the charge point and the EV over the data cables or the transmission cable itself should be encrypted and TLS supported, SSL supported.
So did you guys also implement the part where the negotiation for the charging voltage and current is done using the SMS or just the OCPP?
Okay, this part is for the OCPP, which is communicating with charge point and the server part. The other part, the requirement between the the EV vehicle and between the charging station, it depends. There are 2-3 protocol is possible. As I said, the plug and charge, which is another one, and another one is there is the proximity sensor and what else? Can you the pilot? Yeah.
You need the meters to communicate, and there are a set of state machines you need to implement as part of the specification. So when is the automotive vehicle is ready to receive, let's say, high current, or is it the charger itself is ready to supply a high current? So there are set of specifications. Maybe go to the previous slide.
But that is a closed source. That's the reason we cannot.
Specifications numbering system. You can say this is all closed source. So once you implement all these specifications, the real charge is so this cannot be open unless we implemented this in the past. Let's say for the customers who are currently maintaining it, but that's all closed portions of stuff. So that in the next slide, I saw that the SMS is also used.
Yeah.
So that is for the communication between the battery and charger.
No, these are all the protocols which is supported by the Zephyr, which is used for the metering. For example, if I have to monitor the how much charge or the energy is being consumed by the EV, and I have to report it back for the billing or the other back end cycles. For that, this energy meter really exist over either CAN or SMS protocols, and also the PWM and other protocols. So by using this SMS protocols only, you can negotiate with the energy meter to get the voltage or the how much energy it's being delivered, and also even to turn it on or off and all this.
That comes from the car, right? Or the vehicle, right?
No, it's part of EV. The charging station. It's part of charging station. Charging station is the one which will deliver the power to the EV. So charging station has the whole control. When just I plug in the EV, the cable to the charging station, it should not deliver. Okay, it has to monitor everything.
Suppose the battery heats up.
Yeah.
So the battery inside that's
Okay.
So
Okay.
that will be
Yeah, I got it. So this is the fault communications. Those is, as I said, it is not, the cable is not just only to deliver the power. Also, there is a communication between the EV and the charging pad. So EV has to tell, okay, my battery is getting heat up. Just either limit the current, or else you just stop the current. So this is a communication. So these communications taken over these cables, and the EV charge has to take care. And okay, those are the part of this specification, the close to one, as I said. But
which waveform is it using? Is it using the the SMS itself? Or?
No. It is over that the power line transmission. Power line transmission protocol that I cannot reveal here, because, as I said, it's as a closed resource, the standards. But the Modbus which I have mentioned here is mainly to communicate the metering system which is available on the charging station itself. Do you have any questions, or can I proceed? Okay. So as I said, Zephyr has a multiple opportunity for, let's say, for internet connection, we have a multiple interface Wi-Fi, Ethernet, or the modem which is already available, and on top of that, we need the transport layer, the HTTP or the TLS connection with socket, and then OCPP native protocol is supported. So we can build or the customize our electrical vehicle supply equipment of the charging station full blown with the Zephyr using the microcontrollers. Okay, and this is mainly for the low to medium capacity EV chargers, as I said, because we need a more distributed place where the car cannot be parked in one place. And then next part is this is for the high performance EVSE with the Linux and Zephyr RTOS. How can Zephyr RTOS helpful for the real-time achievement or the requirement for the charging station, and all other part which I said, the OCPP, or else the user can have a rich look of GUI, and then which again it need a kind of a GPU and demand. All those things cannot be achieved from the Zephyr RTOS or real-time. And one of the advantage of using this is, as I said, the GPU can be used on the application processor, which is based on the Linux, and then user can select anything for the payment, or even the OCPP connection back, and so on. And once the charging is started, it can offload everything to the Zephyr RTOS for the real time monitoring for the metering system, or else the energy, the overcurrent monitoring, the fault tolerance. All these things can be offloaded to the Zephyr RTOS, and then the application which is running on the CPU, or the application proc can be safe to sleep. So which will save the energy in terms of charging station consumption itself. So the so this is considered the one SoC which has heterogeneous systems. So yeah, that's how the M4 core can have the Zephyr RTOS, which is monitoring all this the communication protocol, which is between the EV and the charging station, and the server central system, and the charging protocols, the OCPP and other part, and also the HMI, GUI, everything can be handled over to the Linux. And again, how does these two core, or the two different operating system which will interact together. For example, so when the Linux receives some signal for a start charging using HMI, then it has to be shared to or passed to the Zephyr RTOS so that it can start or give a Modbus signal to the uh, the switch and it can turn it on. So that is achieved over the inter-process communication using the RPC message and Open app, which is already being supported in Zephyr. Yeah. So that's it from my side. Any questions?
So which code was running this Zephyr?
You're asking about here?
Yeah, M4, right?
Yeah, it's M4. It's one of the example that I have shown here, but
so A7 is expected to run next.
Yes. Even Linux can be used to monitor or handle these real-time use cases, but again we have to fine-tune with the RT Linux enabled and so on. And one of the advantages with the Zephyr is you can do the any faulty action immediately in the interrupt context. But in the context with the Linux, it is difficult. Like the interrupt will always in the kernel space, and again it has to be notified to user space either in the polling or something, and also the otherwise if you wants to achieve that in the kernel space, then again it has to be um, the second level interrupt handlers like yeah.
What exactly you are trying to compare with Linux or and Zephyr? Both can be used, right?
Yeah, here what I'm saying is the HMI part and the other OCPP non-critical part can be handled from the Linux perspective because it has the GPU access and everything, so it can give the rich look on the GUI or the display itself, and other real-time communication between the electrical vehicle and charging system can be offloaded to the Zephyr on the M4 so that the actual Linux can go to the sleep.
That's kind of one option.
Yes.
But how much load are we expecting on the real time here? For example, if we do Zephyr with LVGL and use that itself on an M core or an A core, that itself can serve both the purposes.
Yeah, that's true. But the GPU is used here mainly for UI and offloading the CPU itself, but which is not available in the M4 core or standalone microcontroller. That's a purpose we have divided into two vertical, one for the low to small quantity capacity EV vehicle charging, and then the high capacity.
So, on the real time domains, instead of using the Zephyr, we are using the non-options. So, what is the main advantage to adapt Zephyr RTOS in this real time comparison?
Okay, in case of a Zephyr RTOS, as I said, the inter-process communication, the things are already available, and we can use it from the Linux and this. And apart from that, the Modbus and all the support, and it is a like yeah, I cannot make it a direct comparison with the free RTOS because I am less aware of the free RTOS, as I said. So it's from the Linux communities, both the RTOS, and that's it. The main goal here is to emphasize how can we achieve the Zephyr RTOS.
So inter-process communication is based on shared memory.
Yeah.
And how fast? Like, is there any latency perspective?
Okay, it again depends on the shared memory or the mailbox communications. So between the two CPUs.
Yeah, it is based on the SOC. The SOC level, which is the if you're using the external, let's say DDM that is connected external to the SOC. So when you're using this memory for IP, you may get one way. Coming to the internal SOC, has the something like SRAM. So when you're using this memory for application, then the latency different.
So one of the advantages here, we can use the same kind of a stack except the OCPP and other part. We can use the same Zephyr code or the application which can be run on the M4 here for monitoring or handling the critical use cases. So we can have option same code base which can handles for the low capacity and the high capacity, high variant and low variant.
But interesting thing is like it's a multi-core processor. And
yeah, this one is a multi-core processor.
One running Linux and another running Zephyr.
Yes. Any other questions? Okay, thank you.